So one of the big takeaways from the first week of lecture was supposed to be an understanding of the key layers of abstraction that are associated with computer architecture. And referring back to that particular slide, uh, I had mentioned abstraction layers in modern computing systems and had this diagram showing that in its we may have an application that is meaning to communicate with another application, but we know that underneath that goal of an application, what we ultimately have is a lot of messy physics, either messy device physics um, on the physical layer for the semiconductor side of things, or messy physics for physical layer for the networking side of things. That also ultimately involves semiconductors as well, but the analog values traveling along a wire or through the RF space. And we use that term a lot, abstraction or abstraction layers, and I didn't really define it appropriately in this context, right? So abstraction just refers to as a way of simplifying the system or the entity that you're interested in analyzing. Um, Taking what is maybe something comprised of many pieces and thinking of it as just a single whole instead. And that's what we do in all computing systems. And that's why we refer to these things as a stack, as a computing stack, as a networking stack, as an abstraction layered stack. Because we recognize again that underneath that application, there's a number of steps from that application, maybe just a single application again, all the way down to our underlying device physics, which we know can be extremely messy. Even ignoring the physics side and just think of transistors, we may have an application that there's this single task, a single thing that we want to do, and ultimately we're mapping it to this device that's consisting of billions of transistors, right? So we devise these abstraction layers, and at each successive one, it allows us to deal with that complexity by simplifying the model in which we're interested in reasoning about a system. So, as opposed to worrying about individual silicon atoms, which would be crazy, right? We worry about the individual transistors. Well, there's still billions of those, and it's important to study those, it's important to understand those, but we can abstract that further out and look at individual circuit elements. And above that, look at individual logic gates that we may have. And above that now, look at layout of microarchitectural design elements. And now we have that hardware software divide that now we look at assembly instructions and what they're intended to do. And on top of that, then you have your software stack that you learn about in your other courses, from the operating system that you'll eventually learn more about, to the programming language, runtime libraries, compiler infrastructure, to the algorithms that are being implemented, and then ultimately to the actual application that you're interested in ultimately implementing. Um, in general, in computing, a good philosophy is that we deal with complexity through abstraction. That's true of all computing. It's certainly equally true of the networking side of things. That is not the topic at all of this course. But for this course specifically, that's relevant because we are looking at very specific layers of the computing stack and the design and optimization of those layers of the computing stack. And that's specifically the ISA, the instruction set architecture layer, the microarchitectural layer, and the underlying logic layer or logic level representation. That term RTL is a bit of a red herring here, refers to a very specific type of design philosophy, register transfer level design. Think of that as your digital logic layer, and you're perfectly fine throughout this semester. That's the focus of this course. And the textbook does a pretty good job of basically feeding you this one example of instruction set architecture and maybe talking about the fact that other ones exist. And there's different flavors of the same textbook that cover different ISAs entirely. But it is to some extent spoon fed to you that this is the MIPS ISA. We will learn it together in excruciating detail, and you'll know all the ones and zeros of it ultimately. Um, but it never talks that much about the why the ISA was designed in a certain way. And I think if we're not careful, you can come away from this course with the impression is that is what an ISA looks like. That is what an ISA is intended to do, which isn't altogether wrong. But the real world is allowed for a lot more creativity and flexibility with how an ISA could be potentially designed. So I thought we could do that together. Let's design an ISA just as a one-off exercise here, and then we throw it out. We don't use it again, but you can at least see a little bit of that design process for, particularly for an ISA. Let's make sure our terms are in pretty good shape here. Um, I keep throwing out ISA, and we did define it on that slide, but just to make sure. So when I refer to an ISA, that is instruction set architecture. And the word architecture here is maybe a little unfortunate. Um, it is all part of the same big picture concept, but instruction set architecture, your working definition is this is the set of instructions that make something model XYZ processor, a MIPS processor, an ARM processor, an Intel Core 2 quad processor. This is the set of instructions, and here is what they are supposed to do. That is the ISA. So it's got the word architecture in there, but it doesn't have any of that digital logic we think of as architecture as part of it. It's not a physical thing, it is a design spec for here's our assembly instructions. Underneath that is the microarchitecture, and I'll just simplify that microarch or microarchitecture. That is at the layer below the ISA. And for that reason, one ISA can have multiple different microarchitectural implementations. So the ISA says we have this add instruction, and it's a spec for it. We take these two values, we add them together, we store the results somewhere else. The microarchitecture is what says, as part of our implementation spec or our actual implementation, here is how you're going to do that addition. There's going to be a register file that's going to store the values, and it's going to have two ports on it. And there's going to be an adder that's going to take those two values and it's going to do some addition, and then it's going to return the result back into the register file back out. That's one way to do the implementation. Another implementation for the same may only have one port on that register file, and it's going to grab them sequentially and then do the addition and then finally return the result back out. There's maybe infinitely many variations, but that's how we're going to actually get the assembly instructions to do what they need to do. That's the microarchitecture. And there can be many such ones for a given ISA. And there tend to be in practice. And then below that again is our logic level. We now know based on our microarchitectural design decisions that we need an adder and we need a register file. And now at the logic level, we now have to do our 281 task. Well, how do we implement that register file? How much space is it going to ultimately take on the chip? How do we get those two ports working? We have an adder. Well, there's an infinite number of ways to implement addition. Not literally, figuratively. There's many different ways to implement addition. Which one is best for our microarchitectural design decisions? How many cycles do we want it to take? How much power do we want it to consume? How much chip real estate do we want it to take? So those layers are relatively independent of each other, but certainly decisions made at one layer influence the layers above and below it. Our choice of ISA, and ISAs change relatively slowly, but our choice of ISA will ultimately very much affect our implementation at the microarchitectural layer and potentially below. And likewise, our microarchitecture will influence, the performance of our ISA's implementation, as well as influence what logic level decisions we have to make here. So they're all intertwined. Computer architecture, and certainly the focus of this course, is all three of those things. We won't be building a lot of custom adders. That's more of a 281 type of topic, or even a EE465 type of topic, a digital VLSI course. But we gain some appreciation of the different types of ways we can do adders. When we get to become more comfortable with VHDL, we recognize, well, the A plus B operator in VHDL is going to probably do a better job than anything we could compose ourselves this semester. So as I mentioned, the book kind of sort of spoon feeds at one particular ISA for you. Let's ignore that. We haven't covered it yet, but let's ignore it anyway. And let's look at an individual application and try to design our own ISA. Now, this is me doing all the talking, but I'd like you to think about these questions that I raised in a somewhat rhetorical manner here. The application I thought of is not like an app in that sense. It can be thought of as just a single, signal processing application where I am wanting to calculate some output Y. and y is going to be some function of an input x. Yes, it's math, but it's not hard math. X cubed minus x squared plus x minus 1. Um, where what is x, what is y in physical reality, it doesn't really matter, but we could think of x as being some sort of sensor input. It's a temperature sensor. And y is some sort of maybe display output. I hope everyone can read my handwriting. I can tell the tools to attempt to magically improve my handwriting, but I bet it's gonna get really confused when I try. Not terrible. We'll just stick with the handwriting. Um, Again, that's our application. It's not doing much. That's that terribly complicated. It doesn't have really complicated control. When we talked about the parts of a computer and I mentioned data path and control, this is entirely data processing. It's not making any decisions, at least not in its current form. We then, not being told that we have a particular ISA we have to use, then it's now up to us to decide what is necessary for our ISA. And a perfectly valid answer, and this point is not just a hypothetical point, it's a very common thing to look at a particular application and say, that application is so common and so important, not that this one is, but for other theoretical applications, it's so common and so important that for our ISA, for an implementation at that microarchitectural layer for that application, we should dedicate an instruction specifically for that application. I don't know what we want to call that instruction. Uh, it's kind of hard to say for this one particularly. They tend to have mnemonics for everything. Take X and compute everything. That could be a name of an ISA for our ISA design. It's a single instruction that takes in the value of x and calculates x cubed minus x squared plus x minus 1. That's a perfectly valid design decision. We still then have to figure out, microarchitecturally, what does that look like, and then later at the logic level. But at the ISA design level, we said, well, this is important to us. We want to design processors that can do that efficiently. We're going to build basically an application-specific processor that is going to be very good at doing this. Let's briefly discuss the potential advantages and disadvantages of that design decision for the ISA. Again, ISA, what instructions are processors required to support and what do they do? In this case, it's kind of self-identifying. What instructions are there? There's one. What does it do? It does everything. It takes X and computes everything. It computes the entire application. The advantage, I think, are pretty clear. Let's be a plus sign there. The advantages, I think, are pretty clear in that it's simple. And it should be pretty efficient too, right? We haven't talked at all about what that means from a microarchitectural perspective yet. But I think it makes some intuitive sense that if I just have one instruction and that's all that instruction, that all that processor is required to support, I should be able to dedicate a lot of engineering hours towards that. I should be able to build a pretty efficient implementation, and certainly it's simpler. It gets points for simplicity here. The programmer's job is really easy. They write just one instruction and they're done. The compiler has no job to do basically here either. It is potentially cheaper, potentially. A little bit of a caveat there. If I know my goal is to build a processor that is doing this application and we believe that this application is important enough, then this should be a nice low cost solution versus something that could do all sorts of things. But that also leads to one of the kind of, I think, obvious drawbacks of this kind of approach. This is a processor for this particular ISA that's addressing a very narrow market, right? If you're interested in y equals x cubed minus x squared, yada, 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 this is the chip for you. And if that's not what you're interested in, you're never going to purchase this chip. So it's a niche product, very likely here. So it's identified a pretty narrow market for it to be able to be sold in ultimately. And we do care about that, right? And then otherwise, just in terms of, you want to call that programmability or expressiveness of the ISA. It doesn't seem like a great ISA choice in that sense. That maybe there's other stuff you can do with combinations of this assembly instruction, and there are processors that are basically essentially single instruction computers. They tend to be toys, though. It doesn't seem like it's very configurable, at least in its current form. Reusability is also a problem, and by and large, there is an explicit trade-off there, right, between the efficiency of our ISA, excuse me, and our expressiveness or programmability. That tends to be an explicit trade-off. That the more single function something is, the more efficient it's going to be. So you wind up with very narrow processors or very narrow ISAs that can do a very few things extremely well. Or as you have a curve here, and it may not be explicitly of this shape, but roughly has that inverse relationship here. As you have a broader ISA that has more programmability to it, more instructions is one way to think about it. Your efficiency of those instructions is going to fundamentally decrease. And for the same reason we talked about, for a single instruction or for a relatively small set of instructions, more resources can be dedicated to implementing those. We'll talk about this in other contexts later on, um, but that's sort of an explicit trade-off that's always going to be there. We refer to so-called general purpose processing or general purpose processors. That used to be a very important distinction for a processor. Um, it's kind of become more meaningless over time, but that's referring to a processor that sits somewhere around here on the programmability efficiency space, where highly programmable has a lot of instructions, so it can do a lot of things relatively well, but not anything individually all that necessarily great. So that is one possible solution for our ISA here. If that was it, then we could be done and we can move on. I would mention, I think some of you are looking at this equation and you're recognizing, and it just occurred to me as well, that we talk about the application layer of our compute stack, and immediately underneath application is the algorithmic layer, right? My application tells me I need to compute this. My algorithm gives me some insight as to how I can do so efficiently, and we can do a little bit of factoring out, right? We can in fact factor out x from most of those terms there. And what do we get? We get x squared minus x plus 1. I know, I told you there would not be very much math. Um, then we can factor that out as well, right? We can do it the other way. We can do x squared. Let's reverse that. We can factor that out with the x squared term, right? Right? We can, of those first two terms. Told myself there'd be no math. If we factor out x squared here, then we get x minus 1 plus x minus 1. And then we have that common term there. So we can get that whole expression equal to x squared plus 1 times x minus 1, right? X minus 1, x minus 1, we factored that out there. Um, that could potentially lead to some efficiency, right? If we compare that version of the equation for our application versus the initial version, this has 1, 2, 3 multiplications and 1, 2, 3 additions. This has 1, 2 multiplications and 2 additions. So in theory, at least in terms of computational steps required, it is slightly more efficient. So that's our algorithm stage. We've done a slight optimization there, a very slight one. But then we can think about what instructions, separate from this very simplified single instruction computer version, we would necessarily need for this. There's no wrong answer here. We're designing this, and I'm giving you my thoughts of what may work here. But again, the ISA is the instructions and what they're supposed to do. At the very least, we know that we have a sensor value that we're reading and a display value that we are writing back out. So at the very least, we need some way of loading a sensor value, and we need some way of storing a result. And you'll find that tends to be a pretty universal thing in ISAs, that some way of, and we talk about the device as input device and output device as one of the five components of a computing system. We need some instruction to load from the input, some sort of instruction to write back, store back out to the output. So we need something, whether it's called load store, that's one possibility here. I mentioned that we do have multiplications inherent in this. We could, in theory, do multiplication via repeated addition, but that's going to lead to a fairly long assembly program. So let's assume we have a multiplication instruction because it looks like the application needs it, even with our slight optimization. And then we have that addition that we have here, so let's make sure we have an add instruction as well. That's not a full description of the ISA, right? That's certainly not a spec. That's the name of four instructions that do four different things. But we can start to hand wave the rest of it, right? At the microarchitectural level, we also then would know what kind of things that we would need to be able to implement this processor ultimately. So I'd say these are the things we need. This is the microarchitectural stuff we would need to implement this processing application. We know we need those I/O devices. We won't talk any more details about what that sensor would look like or what type of bus would be needed to read from it. Ignoring that for now, we need those actual devices. We need, as all computers tend to need, some place to store the results. So we would need memory. We need to put things in memory, whether that's a register file or SRAM storage. Let's not worry about those details yet. Those tend to be logic level details. And if we're doing multiplication, we probably need a multiplier. A logic element that presumably takes two values, multiplies them together, and stores the result. And then we would also then need an adder as well. So with those microarchitectural elements and some hand-wavy definition of our ISA, we can then go and write our first assembly program for the course that is attempting to implement this application here. So first off, we would certainly need to load the value from our sensor input and put it into memory. We're defining the ISA as we go here. Let's say that's the destination, memory location of 1, some address in memory, and load X, whatever X ultimately correspond to if it's a sensor input. Now you may say, Joe, why do we even need to do that? Why can't we just have an add instruction that operates directly on sensor inputs? There's no reason we can't. We just didn't. We created an explicit load and store instruction in this version of the ISA. I can envision for this very simple application a processor that doesn't require those. But I think we need some intermediate storage even to implement this. So we've loaded X, and we need to now calculate X squared. So if we want to add a little comment on the end here, what we're doing here, we've taken this value of X and we've stored it to memory location of 1. Now we need to multiply that X by itself. So again, we're kind of defining the ISA as we go. Let's put the destination first. Store the result in memory of 2, memory of 1. That's where X is stored, and we're multiplying it by itself. So we need to maybe mention memory of 1 twice. We could have had an instruction that is like a squaring instruction. That would have been perfectly fine. But then we would see we would also still need a multiplication instruction to support that. So having that multiplication instruction makes some sort of sense. Now, if we wanted to leave a comment for where we are here, now we have X squared is what's stored in memory of 2. So we've grabbed X, we've calculated X squared. We can then now calculate X squared plus 1. And that would be using our add instruction. In this case, we would want to store the result in another temporary value in a location, memory of 3, the value in memory of 1, and the actual value of 1. And you may be saying, well, does your ISA that we've designed allow us to add 1 to a memory value? Well, it's got to. We need to have a way to be able to add constants to get this to work. Lots of caveats are possible here. You may now say, well, we don't need x squared anymore. Why don't we just store the value back in memory of 2? We could have. That's perfectly fine. I do see the mistake here, right? It's memory of it's memory of 2 that we're grabbing. It's x squared that we're taking, and we're adding 1 to that there. X squared plus 1 is now stored in memory 3. So all those questions that may be ringing your head are perfectly valid. We've designed the ISA as we've gone due to necessity for this application. We have only realized just now we need an add instruction that allows us to add 1, whether that's an add immediate, whether it's just baked into the add instruction. Well, that's for us to decide. Take a minute though. I won't pause the video, but just take a minute and breathe. And certainly if this is confusing, that's fine as well. Think about what may be next. I'll tell you in just a moment, but think about what would then be next. We've just calculated x squared plus 1. What should our next instruction be? And if you said we should calculate x minus 1, I'm not saying you're right. You are right, but you're following my thought process at least is what I was thinking of for here. Let's just keep using memory. Maybe an assembler will come in and will make more efficient use of memory. But now we're back to using mem of 1 because we need x again. And now we're adding negative 1. Hey Joe, you say, are we allowed to add negative numbers in this add instruction? Yes, we are, of course. We're designing this as we go. Now we've calculated x of 1. Now we need to multiply those two temporary values that we've created. So now we're using the mult instruction again. Let's put that in mem of 5. And that's now mem of 3 times mem of 4. I won't even put the comment there. I think it's self-evident now. We've calculated x squared plus 1 times x minus 1. We're not quite done, right? We've calculated what we wanted to calculate, but now we need to store the result back out into y, that value of mem of 5. So that's our ISA. That's our somewhat arbitrary ISA. We came up with it kind of as we were going here by necessity for the particular application. We can compare and contrast that ISA to the single instruction ISA. We can compare and contrast that ISA to the MIPS ISA later in the semester as well. We can see that it's lacking some things. This processor that would implement this ISA would not be able to do any branching, any control flow, any actual decision making. We'd be making a calculator. It would be possibly a fairly limited calculator, but it'd be less limited than the single instruction processor version of the same that can just take X and calculate everything. If my algorithm changes tomorrow, that processor is completely out of luck, whereas ours, we would just write new code for it, right? We would just change the order or the variance of our assembly instructions to do so. We should look at MIPS as just one other instance of that design space for ISA. It's a well-designed one. It's got a nice textbook associated with it. It's one that is in popular use, not as popular as others, but still relatively popular. So we won't focus as much as to why the MIPS add instruction looks a certain way, but we'll really be focusing a lot more on understanding the MIPS ISA, becoming adept programmers in the MIPS ISA, and then finally, ultimately, understanding the microarchitectural design space for the MIPS ISA, and that's going to take us a good chunk of this semester. So let me know if you have any questions about that. Post on Discord if you do. Otherwise, look forward to seeing you in the next class. Thanks.